In this video, we will discuss about the basic principle of operation of DC generator. In order to understand this basic principle of DC generator, we should clearly understood what is meant by a DC generator or what is meant by a generator. Then we should know about Faraday's law of electromagnetic induction. Then what are the types of induction? Then another important term called excitation. So after discussing these important prerequisites, then only we can understand what is meant by what is the basic principle of operation of DC generator. First of all, what is meant by generator? It is a rotating machine which converts mechanical energy to the electrical energy, where electrical energy can be generated. And the next thing is what is Faraday's law of electromagnetic induction. This law states that whenever there is a change in flux, and if a conductor is linked with that flux, change in flux, then an EMF will be induced in that conductor. So this is called Faraday's law of electromagnetic induction. In this, what are the important thing is, there should be a flux, a production of flux, and that flux should change. It should change, and we need a conductor. A conductor should be there, which should link with that change in flux. Then only an EMF will be induced in the conductor. Coming to different types of induction. What are the different types of induction is? It can be broadly classified into two types. One is static induction, and the other one is dynamic induction. What is the static induction and what is this dynamic induction is? Concept is same. Faraday's law of electromagnetic induction only describes about the EMF induction. But how to bring the change in the flux? If the change in the flux is already because of the change in the current by which it is produced, then the induction will be static induction. Or otherwise, if the flux is constant and you are changing the flux by moving some certain things, by moving the conductor or by moving any other the armature or related to that, then that is nothing but a dynamic induction. You are changing the flux by disturbing the flow of flux. Then it is nothing but dynamic induction. In most of the rotating machines, electromechanical energy conversion machines, usually we used to use electromagnets for the production of flux. We won't use any permanent magnets. We are going for electromagnets, particularly when the size of the machine is too large, we'll go for an electromagnet. So excitation is nothing but the concept of or the phenomena of production of the flux, just the production of the flux by applying an electrical supply to the coil. For example, let us assume I am taking a coil like this and I am applying a DC supply to this. Then this DC supply will circulate a current which is also a constant, because the nature of the current will follow the nature of the voltage. If the voltage is constant, then the current will also be the constant. Then this current, when it is flowing through a coil, it will produce a magnetic flux. That magnetic flux will be constant. This is called as excitation. The phenomenon of applying an electrical supply for the production of the flux is nothing but the excitation. In case if I apply a AC supply, if the voltage is AC, sinusoidal, let us assume sinusoidal, then it will circulate a current which is also sinusoidal. As I already told, it will follow the same. The nature of the current will follow the nature of the voltage. So the current will also be sinusoidal, and when it flows through a coil or any conducting medium, it produces a flux. Now this flux is variable. This flux is variable because your current is variable, this flux is variable. So this is nothing but the excitation. These are all the prerequisites we should understand to understand the basic principle of operation of DC generator. So now we will go for the So as I already told, in case of DC generator, what is the type of induction taking place is, it is dynamic induction. Because here the flux is produced by a constant DC supply. Thereby, since the flux is constant, it is not going to change on its own. We have to make the conductor or the armature in which we are placing the conductor to disturb the flow of flux, and thereby we are creating the change in the flux. And because of this change in flux, an EMF will be induced in the conductor which is linking with that flux. And that type of induction is called dynamic induction. And the EMF induced in this type of dynamic induction is dynamically induced EMF. It is called dynamically induced EMF. So in order to understand the basic principle of operation of DC generator, let us take a single loop coil with the two permanent magnets. Just with two permanent magnets and one single loop coil, we can understand in a better way the basic principle of operation of DC generator. So let me draw the diagram. Let us assume AB is connected to, this is the rectangular coil and this is the pole, north pole and south pole, which produces the necessary magnetic flux. As we told already, for Faraday's law of electromagnetic induction, the very important thing is flux. So the flux is produced by the permanent magnets, and this is the coil in which we are trying to induce an EMF. Initially, let us assume we are using a slip ring so as to connect the coil which is going to rotate, and on the slip ring will place the brushes. So what is the purpose of brush here is to collect the current which is circulated by the induced EMF in the coil and distribute that current to the external load, which may be static. But this is rotating. The coil and along with the coil, the slip rings all are rotating. But your brush should be static. So it will slide over the peripheral of your slip ring. For example, let us assume this one as brush and this is your slip ring. If I place like this, if the slip ring is fixed, it is rigidly fixed to the conductors and it will rotate along with the conductors, but your brush will slide over the peripheral and its position won't change. It won't move. It is fixed. Thereby, since it is having a continuous contact with your slip ring, it can collect the current from the slip ring. That is whatever it is getting, whatever the slip ring is getting from the conductors. The current will be collected by the brushes and it will be delivered that current to the external load. So here in the rectangle loop, another important point which I want to stress is this AB and CD, it is called as coil sides. These are all called coil sides, or we can call it as conductors. So it is clear that for one single loop there are two conductors. AB and CD are the conductors where the EMF will be induced, useful EMF will be induced, and that EMF will be circulated. Now let us assume this is slip ring 1 and this is brush 1, this is slip ring 2 and this is brush 2. AB conductor, let us assume it is rigidly fixed to the slip ring 1, and CD's conductor is connected to the slip ring 2. Now the external load is connected to your brushes. Let us assume this is the external load, RL load, and let us mention the terminals as M and N. Okay. Now let us assume this is the position, initial position. Let us assume it as theta is equal to 0, first position, where the plane of the coil, this is the plane of the coil, and plane of the poles all are in parallel. They are all in parallel. And now we can represent our flux lines, which is flowing from north pole to south pole. Always the flux lines will flow from north pole to south pole. So these are the flux lines, let us assume, which is flowing from north pole to south pole. Now, if you see this condition or this position of your rectangular coil, now the plane of the rectangular coil is parallel to the plane of the poles. The flux linkage is more, but the disturbance caused by this position of your coil to the flux is very less. Practically it is zero. That is, your change in flux in this position is zero. Thereby there won't be any EMF induced in this position. In this position, no EMF will be induced. Let us draw the, with respect to the position, let us represent our EMF. At theta is equal to 0, the EMF induced is 0. And let us assume by some external means, through an external agent, let us assume we are rotating this in the anti-clockwise direction. We are rotating the whole coil in the anti-clockwise direction. And straight away we will go for the second position. We will assume the second position as theta is equal to 2. Theta is equal to 90 at 90 degree. That is, now the positions of your so if this coil is going to rotate in the anti-clockwise direction, CD will go up and AB will go down. Thereby, this side where north pole is there, here CD will be there, and it is continuing. The rotation is continuing, and this is AB. And as we already saw, AB is connected to slip ring 1. It is rigidly connected to slip ring 1. There is no change in it. But the thing is, the slip ring will also rotate along with the coils. So CD is fixed to the slip ring 2. So this is slip ring 1, and this is slip ring 2, brush 1, B2. So in the external condition, it is connected to M and N external load. Now if you see the position of your coil with respect to the flux lines or with respect to the poles, the plane of the coil is just perpendicular to the plane of the poles. Thereby, the flux linkage, the total flux linkage with the coil is less, but the change in the flux is very high. It is the maximum. Change in the flux is maximum. And we know already the EMF induced is directly proportional to dphi by dt according to Faraday's law of electromagnetic induction. According to the Faraday's law of electromagnetic induction, we already saw that the EMF induced is directly proportional to the change in the flux. Here in this position at theta is equal to 90 degree, the change in the flux is maximum, the maximum. So in between these two, the positions, let us assume at theta is equal to 30 degree, 45 degree, 60 degree, like that. If you say, gradually the change in the flux or the disturbance produced by the position of the coil is gradually increasing. When it reaches 90 degree, it is a maximum. So now I can draw the change in the flux, which is nothing but if the change in the flux increases, the EMF induced will also increase. So let us assume at 90 degree, it reaches the maximum. So in this curve, like this curve, the EMF is increasing in this manner from 0 to 90 degree. Now, once again, if it is continuing for the another 90 degree, that is at theta is equal to 180 degree, which is the third position, at theta is equal to 180 degree. What happens? You will get the same position, but the position of your AB and CD will change. This will be AB and this will be CD. Okay? Because of continuous rotation of your coil. And AB is connected to, it is rigidly fixed to this one, but CD is connected to this one. So this is the position of 180 degree. Okay. So half of the rotation is over. Before going to the next half of the rotation, we will discuss about the direction of the current which is circulated by the EMF induced in the coil. Now if you analyze in the first position, that is at theta is equal to 0, I told that there is no change in the flux and thereby the EMF induced will be 0. Similarly, at theta is equal to 90 degree, when the plane of the coil is perpendicular to the plane of the poles, the maximum amount of EMF will be induced because of the maximum amount of change in flux has occurred. Because this position disturbs maximum amount of flux. Thereby the EMF induced will be very high. But once again in this position at theta is equal to 180 degree, it is similar to your the theta is equal to 0 degree. As far your variation in the flux is concerned, it is same, almost same. Your plane of the pole is parallel to the plane of the coil and thereby flux linkages will be more, but the change in the flux will be less, very less. So in this case also you will get the EMF induced will be 0. So from 90 to 180 degree, gradually the EMF induced reduces. Why it reduces? Because of the change in the flux is reducing. It totally depends upon the position of your coil. Now we will discuss about what is the direction of current circulated by this EMF induced between the 0 to 180 degree in this case. Now, in order to represent the current direction, we should mark the arrow to represent in the conductors. We should represent our arrows to represent the current. So for that, usually we used to take the Faraday's law of electromagnetic, the Fleming's right hand rule to understand the direction of current. We use the Fleming's right hand rule. What it states is, let us assume the Fleming's right hand rule like this. So we need 3 fingers for that. One is thumb, forefinger and middle finger. So the forefinger represents your magnetic field, the direction of the magnetic field. So as per our diagram, the magnetic field is flowing from North Pole to South Pole, and the conductors in the magnetic field, in the North Pole, influenced by the North Pole, if it moves upwards, then according to this Fleming's right hand rule, the current in that particular conductor should come out. It should come out. So here, if you see, according to the direction of rotation, that is anticlockwise direction of rotation, and the CD is the conductor which is influenced by the North Pole, and if you see, it is going up. When the total coil is rotating like this, CD will go up. Thereby, according to the Fleming's right hand rule, the current will come out from the CD. So it comes out, since CD is connected to the slip ring 2, it will come out via the slip ring 2, and as the important function of your brush is to collect the current, it will collect this current and it will pass the current like this, via like this. So in the AB conductor, the current will flow like this. So in the external load, the polarities will be like this. M will be positive. This is M. M will be positive and N will be negative. Okay. So this is how to represent our current direction by using the Fleming's right hand rule for this DC generator. Now half of the cycle is over with the slip rings. Let us assume the last another portion. After theta is equal to 180 degree, once again if it rotates for 90 degree, theta will become 270. It will become 270. In that portion, this is the fourth portion. The coil will be like this. Now AB will be on this side, which is under the influence of North Pole, and CD will be under the influence of South Pole. But as already it is fixed, there is no change in that connectivity between the conductors and the slip rings. Now once again, if you apply the same Fleming's right hand rule to mark the current direction in the conductors, since your conductor AB is now under the influence of North Pole, the current direction will be like this. It will come out, as I already mentioned, like this. So the conductor which is under the influence of north pole is AB. In that conductor, now because of the rotation is anti-clockwise direction, it is going to move upward. Then the current in that particular conductor will come out. So it will come out like this. Since it is connected, rigidly fixed to the slip ring 1, via the slip ring 1 it jumps to the brush B1, then flows like this, then enters via the brush B2, then via the slip ring to the CD, conductor CD. Now if you see what is the polarity of your external load means, this will be plus and this will be negative. Terminal N will be positive and M will be negative, which is contrologically just opposite to the polarity what we obtained when theta is equal to 90 degree. So if I mention that at theta is equal to 270 degree, let us assume it reaches the negative. Magnitude wise it will be the same. Whatever the magnitude you are getting here, you will get the same one, but it will be in the opposite direction. The EMF induced will be opposite direction. Now, if you see the waveform, it is not DC. It is not the DC voltage, it is the AC voltage. So what is the point we should understand here is, even though it is a DC generator, the actual EMF induced in the conductors or in the coils is purely an AC. It is not DC. If you want to make it DC, we should rectify it. Using some means, you should rectify it. So for that, these slip rings should be replaced by another important device called split rings. We should use a split rings in order to convert the AC induced EMF to the DC. And we can apply that DC to the external load. So for that, we should replace the slip rings by the split rings. So what is that split ring is? So split ring is nothing but a cylindrical shaped ring which is cut into two halves, like it is called as segments. Here there are two segments. These two segments are combined physically with the help of a mica in between. So they are physically intact. These two segments are physically in contact, but they are electrically isolated. There is no electrical connection between the two segments. And the brushes should be kept just on the surface of your split rings. It is not fixed to the surface of the split rings. Instead, it will move along the peripheral of the split rings. That is the arrangement. So with the help of the split rings and the brushes, we can convert the EMF induced, which is actually AC, into DC, and we can feed the DC to the external load. But here there are only two segments, as there are two conductors. For example, in the practical case, if you are using many number of conductors or many number of coils, then the number of segments will also increase. Number of segments in the split rings will also increase. Then it is commercially called as commutator. It is called as commutator. Now let us replace it and we'll try whether it is converting the AC to DC. We'll check it. So now we'll check with the we'll replace the slip rings with the help of split rings. So this is segment 1 and segment 2. The brushes on this side is, let us take B1, and this side is B2. So B1 is fixed to the terminal N, B2 is fixed to the terminal M of the load. But B1 and B2 are not fixed to the split rings, instead it is going to slide over the peripheral of the split rings. When the split rings is going to rotate along with the coil, it will just slide over the peripheral of the split rings. It is not rigidly fixed. But the conductors will be rigidly fixed to the segments. Let us assume conductor AB is fixed to segment 1, conductor CD is fixed to the segment 2. So as far as this position is concerned, we already discussed about the current direction in the CD conductor, which is under the influence of north pole and which is moving upward because of the anticlockwise direction. The current will come out like this, jumps to the split ring segment 2, and from 2, since B2 is in contact with the segment 2, it will jump to the brush B2, travel in this direction, and flows like this. Thereby, M will be positive, as we already discussed, and N will be negative. In the same manner, here also we will replace the slip rings with the help of split rings in this condition. So the position of your brush won't change. It is fixed. B1 and B2 is fixed. B2 is connected to the load terminal M. B2 is connected to the load terminal M, and B1 is connected to the load terminal N. But if you see, now the AB is already told, AB is rigidly fixed to segment 1. This is segment 1. Position of the segment 1 is changed now with respect to the theta is equal to 90 degree. And CD is rigidly fixed to the segment 2. CD is rigidly fixed to the segment 2, as already we told in the here. So the position of the segments of the split rings is changed, but not the position of your brushes. Now the current flow, if you analyze the path of the current flow from the AB conductor, it will enter the segment 1. From the segment 1, it will enter the brush, jump to the brush B2. Via the brush B2, it will travel like this